Welcome. In this video lesson, we're going to take a look at a qualitative analysis involving finding equilibrium points, generating phase lines, and discussing bifurcations. So, an important model analysis that we often like to conduct is called an equilibrium analysis. And an equilibrium analysis is an analysis involving equilibrium points, which is any value of the dependent variable y equals some value that makes dy dt equal to 0. So if you think about in context what this means, if dy dt is 0, then that indicates that there is no change in the dependent variable. So basically we are in an equilibrium state. So if you have a population in which dy dt equals 0, and we should say that this is the case for all t, that is for all time, it's a value of the dependent variable that makes the rate of change 0. We then describe what happens to dy dt for y below that value and for y above that value. So if there are multiple equilibrium points, then we basically do what you might think of as the first derivative test, where you look at all the values or all the intervals surrounding the critical points, which is really what these are. They're critical points. And you look at the sign of dy dt is the function increasing, decreasing, or constant. And this is called a qualitative analysis because it describes the characteristics of the solution function. We're not actually really solving the differential equation itself. In some cases you can't. In some cases you just want to conduct this quick analysis to gain more insight about your solution. So here's a problem we looked at in the previous lesson. Suppose you take out a loan at 1% per month. You make monthly payments of P equals $100. Conduct an equilibrium analysis for this model, which when P was 100, we had 0.01y. That's the interest component, the inflow of money increasing your balance. But then you're taking away $100 from that balance. You're basically paying it off. So to conduct this equilibrium analysis, we want to find the values of the dependent variable. In this case, that dependent variable is called y, such that dy dt equals 0. So what we want to solve is, we want to solve this equation here, 0 equals 0.01y minus 100. And then if we rearrange this simple equation now, and we add 100 to both sides and divide by 0.01, we get y is equal to 10,000, or y is equal to 10,000. Now, if we look at y equals 10,000, what's happening here is we're basically saying that when y is 10,000, in other words, your balance in this account is $10,000, you take out a $10,000 loan, and you make $100 payments, your balance is not going to change at all. We found out now that $10,000 is 1% of 10,000 is 100. So in this term here, we're adding basically 1% of $10,000 to your balance, and 1% of 10,000 is 100. So you're being charged $100 in interest, but you're making a $100 payment, and so your balance will never change. Now, if we kind of do a first derivative style test, and we draw a number line here, and we say that this is really the y-axis, and that when y is $10,000, we are in equilibrium. That is, the balance is not changing. But what happens if y is just slightly bigger than 10,000? So if we pick a value to the right of 10,000, for example, at y equals 11,000, and we plug that into this equation to see what is the sign of dy dt, we get 0.01 times 11,000 minus 100, and that is going to come out to a positive 10. And so what that means is really we don't care about the 10, we just care about the fact that the sign is positive. And so that means that dy dt is bigger than 0 for all values to the right of y equals 10,000. And we can do the same thing at a value less than 10,000. Now the reason that we only need to check one particular input into this function on each interval is because the only way for a different derivative to change signs is to pass a critical point or to pass some sort of break in the graph like an asymptote. This function and most of our functions are defined for all y and t, and so it's not really a problem. But if we pick something like y equals 9,000, then we're actually going to get dy dt is negative 10. And so the fact that is negative is what's important over here, and that means that off to this interval, dy dt is less than 0. So what does that mean? Well, that means that if you take out a loan of $10,000, you'll never pay it off. If you take out a loan bigger than $10,000, well, now your balance is going up. If you took out a balance of $11,000, then your balance would actually go up by $10 per month. So here, your balance is growing, and you'll never pay off the loan. And here, the balance is decreasing, so you will pay off that loan. In other words, you shouldn't, if you want to make a $100 payment and you're being charged 1% per month in interest, you would not want to take out a loan of anything near $10,000. Now, you don't get to choose your payment, but just for the sake of argument, we're making this discussion. Let's take a look at another one. This is also something that we took a look at, and we did find out that P equals 100 was basically the biggest payment you could make for a loan that we classified as being a $10,000 loan. So notice that this quick little analysis here gave us the same level of insight that having to solve this entire model by using separation of variables did. Now, we got the gist of things here when we actually solved it. We had a function to plot. We don't have a function to plot here, but we were able to make some pretty powerful conclusions. So this is a model where we said, suppose 30 grams of a toxic substance enters a 10,000 gallon pond each minute through waste runoff from a chemical company. To keep the water level constant in the pond, water leaves the pond through a stream at 20 gallons per minute. We found in a previous lesson that dy dt equals 300 minus 0.002y. Conduct an equilibrium analysis. All right, so once again, we'll set this thing equal to 0, and we'll solve. And so this is just a two-step equation. So we want to do 300 divided by 0.002. It looks like I have an extra 0 here. There should be 30 minus 0.002. And this, when we solve this equation, we get 15,000. Now that's a number that we recognize as being a pretty important number in our previous problem. So let's see what's going on here. If again I draw a number line here, I say that these are the values of y that get inserted into here, then I have an equilibrium point here at y equals 15,000. And I want to know, okay, so if I ever have y equals 15,000, in other words, if the pond ever ends up having 15,000 grams of this toxic substance, then it's at a saturation point. There will be, over time, no additional change in the amount of the toxin inside the pond. Now, some will be entering, right? Here's our pond. We have some entering and we have some of the substance leaving, but the mixture in here, if it ever achieves 15,000 or starts at 15,000, there will be no change in the amount of that toxic substance in there. But if we look at a value that is bigger than 15,000, let's say 16,000, and we look at dy dt, if dy dt is 16,000, then we're actually going to end up getting, and you can verify this by plugging it in, a negative value. I'm not even going to worry about the value, the numerical value that I get, because I just care to see that dy dt is less than 0. If we look at another value such that this value is less than the 15,000, say y equals 14,000, then we're going to get dy dt is positive. Okay, so that means that here dy dt is bigger than 0. So if we actually put some arrows on this number line to indicate a little more clearly what's going on, we could say that in this case, because dy dt is positive, well, that means that y is increasing. And if y is increasing, that means it's getting closer to 15,000, which made sense because our initial concentration was 0 inside of the pond, and we saw that over time, what happened is the value of y, if we looked at the y versus t graph for having initially 0, we saw something that looked like this with an asymptote here at y equals 15,000. Notice that we don't have any information here about t. We're not really concerned about it because the qualitative analysis just tells us what's happening. And here, if dy dt is less than 0, that means y is going to decrease, and it's going to decrease closer to y equals 15,000. Again, if it hits 15,000, the amount of toxic substance in that pond, then the rate of change becomes 0, and we are basically at a saturation level. So this is a really powerful analysis. And we've got to be careful because not all ODEs have equilibrium points. I just want to emphasize here that an equilibrium point is a value of y. It's not a value of t, it's a value of the dependent variable such that dy dt is 0. Since t often represents time, time changes with or without us, and therefore values of t can only cause brief moments of 0 slope. An equilibrium point, however, is a value of the dependent variable for which dy dt equals 0 for all time. So let's take a look at one example where that is the case. Consider dy dt equals the product of y minus 1 and t minus 1 and find the equilibrium points, then explain why it is not possible to describe the sign of dy dt for all y above and below the equilibrium point. So what I'm going to do here is I'm just going to draw my y-axis vertically, so same number line as we had up here. I see here that if I set this equal to 0, 0 equals y minus 1 times t minus 1. The only value of y that will make this 0. Now clearly if t is 1, then this whole right-hand side becomes a product involving a 0 factor, but the only value of y that will make this 0 is if this factor here is 0, and that means y is equal to 1. So that's our only equilibrium point, when y is equal to 1. Okay, but what happens if y is bigger than 1? Well, if y is bigger than 1, let's say at y equals 2, then that means dy dt is going to equal 2 minus 1, which is 1, times t minus 1. Okay, so just knowing that y is 2 does not allow me to conclude that dy dt is positive or negative, because look at this. Dy dt can still have an issue in that if t is bigger than 1, then dy dt is going to be positive, right? So if I put in time 2, 1 times 2 minus 1 is positive 1, and therefore I'm going to have a positive slope. But if t is less than 1, so for all moments before time 1, even though my value of y is 2, which is bigger than my equilibrium point, in this case dy dt is less than 0. So the key here is that it depends on y and t. And so just knowing what the equilibrium point is, even though it is the case that y equals 1 is an equilibrium point, what happens when y is bigger than 1 or less than 1 begins to now also involve t. Okay, so anytime this first factor is not 0, like it is when y is 1, then we now have to take into account the extra analysis of looking at t. So usually we don't want to do this sort of equilibrium analysis when the function does involve t, because realistically that value is going to affect the rate of change as well. So another important fact to notice is that when dy dt is only a function of y, that is, the model is called autonomous. Remember, that just means that the rate of y depends only on y, like automatic, autonomous, autoimmune, etc., and does not directly depend on t. Then for all y between any two equilibrium points, dy dt maintains a constant sign, either positive or negative. So what I'm referring to here is back in problems 1 and 2, all we needed to know was the value of y, and that told us everything that we needed to know in order to say dy dt is positive or negative. Why? Well, because the right-hand side did not involve time. Same thing here. The right-hand side did not involve time. In problem 3, which was not an autonomous equation, this one depended on both t and y, we could not conduct this analysis. So we could not conclude that dy dt is always positive for y bigger than 1. Since the value of t is not important in determining the slope, a t-axis is not necessary in understanding long-run behavior, and so we draw a single y-axis, as we've been doing, with the equilibrium points and arrows along the intervals showing the behavior of y. So I'm basically now, instead of drawing this horizontally, what we've done here is we've drawn a phase line, and a phase line just tells you where the equilibrium points are and what the sign of dy dt is by using arrows within the different phases of those intervals. Or you could say phases or intervals. Okay, so here let's go ahead and conduct 4 different analyses. We'll do one for dy dt equals y minus 1. So for dy dt equals y minus 1, we set that equal to 0, we get y equals 1. So that means that if I draw an equilibrium or a phase line, I label the equilibrium point y equals 1, and now I just have to figure out what happens when y is bigger than 1 and when y is smaller than 1. So notice no t, these are all autonomous equations. So when y is bigger than 1, that means this is going to be a number bigger than 1 minus 1, which will be positive. So that means that the value of dy dt is positive, which tells us that y is increasing. Now when y is less than 1, clearly you're going to take a number smaller than 1, subtract 1 from it. That will make it negative, which means that if dy dt is negative, y is decreasing. So we call this, we actually start to classify these equilibrium points as well, and we call this equilibrium point here a source. And the reason we call it a source is because things source away from it. In other words, if you're slightly above or below that equilibrium point, it's very unstable. All the solutions are going to move away. So we often call this an unstable equilibrium point. And we want to know that because this might have implications in different disciplines. If you're not at the equilibrium point and you're slightly nearby it, everything will move away from it. In the second example, we have the same equilibrium point, but now we're going to have different things happening for when y is bigger than 1 or when y is less than 1. So in this case, if y is bigger than 1, 1 minus a number bigger than 1 is going to be negative. Therefore, y is decreasing from up here. I want to label everything here also to be clear. And then when y is less than 1, 1 minus a number smaller than 1 will be positive. And so y will be increasing up towards the equilibrium point. So basically this means that from both directions, if we're near the equilibrium point y equals 1, we're ultimately going to approach it. And much like the water in your faucet goes to the drain in the sink, we usually call this a sink. It sinks all the solutions for initial conditions surrounding y equals 1 will sink into it. This is often called a bistable. It's stable from both directions. In number 3, we have 1 minus y squared. Not surprisingly, we're going to get exactly the same equilibrium point, y equals 1. But in this case, y equals 1, well, it doesn't matter what the sign of what's inside of here is. If you square it, it's going to be positive. So that means we're going to have y is increasing for values above 1, y is increasing for y values below 1. And so since we're stable from one direction, if y starts out less than 1, then y is going to approach 1. But if y starts off bigger than 1, it's going to move away from 1. So we often call this a type of equilibrium point a node. This is called a node, and it's called monostable. And you can imagine why. Mono means 1, so it's stable from only one direction but unstable from the other. And finally here for the last problem, for dy dt equals y minus 1 squared. Sorry, I wanted to put negative y minus 1 squared here. That same equilibrium point is the one that we'll get, except that now you can verify that the slopes surrounding y equals 1 will both be negative. So if y starts off bigger than 1, it will decrease towards the equilibrium point of 1, and then it's stuck in equilibrium. And if y starts off less than 1, it's also going to decrease, in this case down towards negative infinity. And this also is called a node, and this also is called monostable. So you have two types of nodes. Nodes just mean that on both sides of the equilibrium, the arrows point in the same direction. So again, this just tells us what's happening to y over time. We don't actually have time in these equations. We don't know how long it's going to take. For example, in example 4 here, we don't know how long it's going to take if y starts off as a half, how long it's going to take to get to negative 500. This is purely a qualitative analysis. Now, we just described classifying an equilibrium point. and we could classify them as a sink. Depending on what discipline you're in, sometimes people use the word attractor, right? Because this is sort of attracting, it's like sucking all the solutions into it, or bistable. If both arrows point away from the equilibrium point, we say that the equilibrium point is a source, and that was this situation here. Or repeller, you could sort of think about it as magnets with like poles, they're going to repel each other. If one arrow points toward and the other points away from said equilibrium point, then we call it a node or monostable. And there are two examples of nodes. Those are these two. Okay, now you can have more than one equilibrium point. In these models, when we solve dy dt equals 0, we only came up with one, namely because our functions have been linear so far. So let's just go ahead and complete this analysis. We sort of already did this for the loan model. We found that the equilibrium point is y equals 10,000. Now all we'll do is we'll just look at this as the y-axis. We said y equals 10,000 is that equilibrium point. If your balance started higher than 10,000, then your balance would basically continue to increase because you're not paying enough to even take care of the interest charge. But if you take out a loan less than $10,000, it will decay and eventually you'll pay it off. It'll become 0. Now, one thing I want to point out as well is that we haven't plotted the t-axis, right? Let's just pretend that this is the t-axis here. What I would actually be able to draw is just based on this behavior. I don't know the exact shape of the curves, but typically if y equals 10,000 is an equilibrium point, meaning that if you ever have a balance of $10,000 and you make a $100 payment, you're charged 1% per month, your balance is always going to remain at 10,000 for all time. So for this initial condition, y equals 10,000, your balance will forever be 10,000. If it starts off slightly higher, then it's actually going to progressively become more exponential because of the fact that when you're taking 1% of growing values, that amount actually gets bigger as well. And if you start off with a balance of less than 10,000, at first it kind of takes a while to really knock some of that balance off, but eventually you'll start to get exponential decay, and that balance will eventually approach 0. So notice that we could kind of superimpose this t-axis, but it's not necessary because this one phase line tells you everything that you need in terms of long-run behavior of those functions. Now, if you wanted this exact curve, you just have to solve this model and solve it using separation of variables. So it depends on what our task is, which will ultimately determine what type of tool we use. Let's do one more, dy dt equals sine of y. So if we set that equal to 0 to find equilibrium points, well, wait a minute, sine of y we know oscillates. And basically, sine of y is 0 for y equals 0. And let's see, sine, if I look at the sine function, sine of t starts off at 0, comes to 1, back down to 0, down to -1, back up to 0. And this is at pi and 2 pi. So same thing over here. And that's going to be at negative pi and -2 pi, and then at every increment of pi, it again reaches 0. So 0, we'd have plus or minus pi, plus or minus 2 pi, etc. And sometimes you'll see people write it like this. They'll say y equals something like n times plus or minus n pi, or you don't even need to use plus or minus. You could just say something like k times pi, where k is any integer. So that's plus or minus 1, plus or minus 2, 0, plus or minus 3, plus or minus 4, etc. But how do you draw a phase line for this? Well, unfortunately, since this thing goes on forever, you can kind of do this ... on either side and plot a few of those equilibrium points just to show the pattern. Y equals 0, y equals pi, y equals 2 pi, and then here y equals negative pi, y equals -2 pi. Now the question is, what is happening on these different intervals? So we have lots of intervals. We'd obviously need to plug in a value between, say, 0 and pi into the sine function. and see whether the sign of it is positive or negative. But I want to propose another idea. Instead of having to plug numbers in, if I look at this graph here, and this is the dy dt axis plotted against y. Now this is a weird graph to look at because your output is actually a slope. Your input is actually a value of the dependent variable. Therefore, if I wanted to plot this function, I'd have to plot dy dt, my vertical, against y, my horizontal. And what that allows me to do is to say anywhere the portion of the graph is above the horizontal axis, those are all positive values of dy dt. So between 0 and pi, dy dt is positive. So between 0 and pi, I'm going to draw an arrow that points up because y is increasing if dy dt is positive. Now from pi to 2 pi, I see that the dy dt graph is below the horizontal axis, which means dy dt is negative, and that means dy dt is decreasing. Wrong interval. Sorry about that. We actually want that here. There we go. And again, from 2 pi to 3 pi, we see that that portion of the graph is above the horizontal axis. So above here, I could draw an arrow pointing upwards. You probably get the pattern. So back here between 0 and negative pi, the portion of the graph is in the negative dy dt region, in the negative portion here. So it would look like this. And then here, its graph indicates that dy dt is positive. So really these are just alternating, and if you look at these equilibrium points to classify them, this one is a source, this one is a sink, and then a source, and then a sink. And it looks like they're going to be alternating in characteristics. So that's one with infinitely many equilibrium points, and that's perfectly fine. Usually we just indicate it by saying something like, well, there are infinitely many of them. Here's a sample phase line. Good news in a lot of applications is that you're not gonna let y be 3,000 pi, for instance, because likely the domain of your model will tell you, you can't have y values that big, or you can't have negative y's. So this is a mathematical phase line. We have also practical phase lines that only look at equilibrium points that we know are meaningful and part of the reality. So again, if y was a population size, then having negative y's just wouldn't make sense. So again, we do not typically draw phase lines for models that are not autonomous. So if dy dt depends on both t and y, or it only depends on t, we don't draw these. And the reason is going back to this example where if t is involved, then the value of t also has a say in whether dy dt is positive or negative. And so the value of y alone does not allow us to accurately draw a phase line. So at that point, you could try to do it for different values of t, just draw multiple phase lines, but that does not benefit us. It does not add value to our analysis. Now that we've laid the groundwork for the use of phase lines, not only are they simple for autonomous models and remove extra axes, but I also want to put this out there that a lot of times when you do analyses, you try to make the analysis as simple as possible. So whenever you can, omitting an axis reduces the complexity of the information. When we are able to summarize what's going on in a model just based on one axis without having to draw time and say, for all time in the model, dy dt equals 1 minus y. If y is ever above 1, for all time it will decrease until it reaches y equals 1 as its equilibrium point. So having the t-axis in here is not necessary for me to understand. The other advantage of working with phase lines is that we can go back to studying models with parameters in there. So let's say we have some general model. This model is what we call the logistic differential equation, and it's a little bit more realistic than, say, something like dy dt equals 0.1y, because in this model, this solution will always be exponential. It will be of the form ke to the 0.1t. And if you plot that, as long as your population starts off positive, we're arguing that the population will continue to grow unchecked, unbounded, forever and ever and ever and ever. This logistic model, however, is one that limits the population growth. So what we're going to observe in this one is that the population starts off growing exponentially, but then as resources run out, as food supplies run out, as disease begins and competition begins within the species, you actually start to see some leveling of the population. So whereas the exponential model, this one, will indicate forever growth, the logistic model will start to flatten the curve. And we've heard that in society recently quite a bit about flattening curves. All right, so with this model, we think about K as the growth rate parameter. And in this case, we're just going to say it's K equals 0.1, so we get to substitute out a value for K. And C is what we call the carrying capacity. And you'll see why in just a moment, what that means exactly, if you're not familiar with that phrasing. But in our model, you see that we have this parameter in here. And just recall that a parameter is constant for any given scenario. But maybe what we want to do is we want to study how changing that carrying capacity is going to affect our phase line. So how it's going to affect different populations. All right, let's go ahead and execute an analysis of that parameter. So rather than having to solve this, which we could do, and then we could go to Desmos and play around with the value of C, which will inevitably be part of our solution, we could do a simpler analysis and just generate some phase lines and understand how the solution will respond to different values of C. Consider the integer values on the interval C between 1 and 4. Create side-by-side phase lines for these 4 values and describe what effect C has on the phase lines. So let's start off by doing an analysis for C equals 1. So if C equals 1, that means, and I'm going to draw my phase line right above here. So if C equals 1, I'm going to be looking at equilibrium points of 0.1y times 1 minus y over 1. Okay, so to find the equilibrium points, there are a couple of ways you can do this. This one's factorable, but if you wanted to find the equilibrium points, one thing you could also do is graph the differential equation and look at the intersection points or the zeros of that function. So let me go ahead and do that in Desmos real quick. So here I'm going to go ahead and just plot 0.1, and I can't do y, so my x-axis I'll kind of just think about as the y-axis, 1 minus y, x over 1. And if I really zoom in here, I can see that this is my dy dt axis. So this function here is the derivative. This is dy dt. And my x-axis is actually a measurement of y. So we see that when dy dt is in this interval here, between 0 and 1, we see that dy dt is positive. All these values here on this curve are positive values of the vertical axis. If y becomes less than 0, you have negative values. That means y is decreasing. And if you have values of y bigger than 1, we see that all the values on the dy dt axis are negative. So here I can snap to these, and I see that there are 2 points. When y is 0, dy dt is 0. And when y is 1, dy dt is 0. So those are my 2 equilibrium points. This graph clearly allows me to see already that if y is less than 0, I'm going to draw a downward arrow. If y is between 0 and 1, I'm going to draw an upward arrow. And if y is bigger than 1, I'm going to draw a downward arrow. So here we go. Let's draw that phase line. And we said that one of the equilibrium points is y equals 0. The other one is y equals 1. And so we said that in between here we have growth. The population is going to be increasing. Try this a better way here. Let's go with green. And if y is bigger than 1 or less than 0, the population is going to be decreasing. So what we really meant by carrying capacity is that's the most the population can hold. If it becomes bigger than 1, then the population starts to die off and tries to die off back to y equals 1. So we have a sink at y equals 1. That population wants to reach its carrying capacity. It cannot carry more than its capacity. It's like a room capacity. And here we have a source. That's a very unstable equilibrium point, but that's okay. We can't really have populations that are negative anyway. We're just drawing this for completion's sake. Now we'll do the same thing for c equals 2. For c equals 2, the only thing that will change is in our equation here as our carrying capacity value will become 2. And notice that what happened is our equilibrium point, one of them, moved from y equals 1 to y equals 2. So if I actually begin another phase line here, I'll still have an equilibrium point at y equals 0. But now my other one jumped to y equals 2. And we saw that that didn't change the behavior on the inner interval. The population still wants to tend to its carrying capacity, but anything above the carrying capacity causes the population to die off a little bit. Again, competition, resources, hunting, increases in hunting, etc. to keep the population at bay. For c equals 3, you guessed it, we're going to have an equilibrium point 1 at y equals 0, and now 1 at y equals 3. And so what will happen, again, we could graph this and verify, but you'll have populations that want to tend to the carrying capacity, and then of course this meaningless 1 down here. And then for c equals 4, same process, but now I'll have one way up here at y equals 4, and down here at y equals 0. Population will want to increase if y is between 0 and 4 until it reaches its equilibrium. It will want to decrease if we exceed the carrying capacity of the species. And one of the things that we could see is that these carrying capacities, 1, 2, 3, 4, if the population size is in hundreds or thousands or millions, then you could have values between c equals 1 and c equals 2. So we actually could continue to draw phase lines. We just limited ourselves to these 4 values, but we did a pretty powerful analysis here. We just really learned what that value of c does. The value of c just creates a bigger gap between our equilibrium points, 1. What that practically means is there's a larger interval for growth if you have a higher carrying capacity. And what that also means is that in all 4 instances, the population behaves in the same way between the intervals. And notice that the classification of our equilibrium points is still sink, source, sink, source, sink, source. And again, the last one is y equals 4 is a sink and y equals 0 is a source. So here's our analysis for the conclusions of it. If the population is between y equals 0 and y equals c, this analysis of drawing these 4 phase lines revealed that the population will increase towards its carrying capacity. The second thing we observed is that larger values of c result in larger windows of growth between y equals 0 and y equals c. And thirdly, the nature of the 2 equilibrium points never changes regardless of the value of c. Y equals 0 is a source and y equals c is a sink. Beautiful. So having these phase lines side by side was very convenient because we could see how small changes in the parameter affected the long run behavior of the solution depending on where your starting value of y is. Also, again, one other thing we could point out here is if we wanted to superimpose the t-axis, I'll just do this kind of real briefly here, but here if we had the t-axis, if y equals 0, then y equals 0 always. If y equals 4, then y will stay at 4 always. And if you're between these intervals, if you started really close to y equals 0, as we'll see later on, the solution would start to increase exponentially. But then once it reached the midway point, there would be an inflection point here, and the rate of change of the function would start to decrease. And you'd have a concave down segment. So populations would increase in this sort of shape in between here. And we could solve this differential equation and prove that. And if populations started up here, they would exponentially decrease. So these equilibrium points are not just values of y for which dy dt is 0 and the population doesn't change, but they also act as asymptotes, which is pretty interesting. So the last thing we should notice is that the number of equilibrium points did not change, and neither did the behavior in the intervals surrounding them. We say that varying the parameter c does not result in a bifurcation. A bifurcation point is any value of the parameter such that either the number of equilibrium points changes or the behavior in the interval surrounding them changes. Often, however, a bifurcation occurs when there is a sudden change in the number of equilibrium points, which then necessarily changes the behavior and intervals surrounding them. The drawing of a phase line side by side, as we have done, is referred to as a bifurcation diagram. So what you might see in situations like this, a real bifurcation plot in the sciences, is you'll see actually people superimpose and try to connect the dots here. So they'll basically draw a line connecting the equilibrium points here, and then they'll try to draw a curve or a line connecting the equilibrium points here. And so what that does is it just really visually divides the intervals. And so if you had a phase line, say here, that would necessarily kind of complete the graph. So we're kind of turning these one-dimensional phase lines into this two-dimensional drawing, where the second dimension, if you notice, this is now our c-axis, and this is our y-axis. So we're looking at what happens to y as a function of what happens to c. Okay, let's do an analysis where we are going to experience a bifurcation. So suppose we let k equals 0.1 and c equals 4 be fixed values for the population. We want to introduce fishing at a rate of f fish per month. Update dy dt to take into account this flow rate. So dy dt as it stands is going to be 0.1y times 1 minus y over 4. Now I'm going to incorporate an independent term which is going to account for fishing at a rate of f fish per month. Assuming t is in months, and that means that this would already be in fish per month. And so if I wanted to take away f fish per month, if that's now going to represent a brand new outflow term, right? So here's our population. There's already some natural birth and death cycles given by this logistic model itself, but now I'm also going to have an independent extra drain in this tub at a rate of f fish per month. Now I want to understand how this parameter affects the population. When am I going to begin overfishing? Because at some point you can imagine that even with a big enough population size, if you fish too much, then you're actually going to cause dy dt to always be negative. Let's conduct an analysis. Suppose that y is in thousands of fish. Create a bifurcation diagram for f is between 0.05 and 0.08 in increments of 0.01. What do you notice? Is there a bifurcation value somewhere? Can you guess what it is? So let's start off with f equals 0.05. So I'm going to draw a phase line for that, and all I'm going to do is I'm just going to come over to Wolfram Alpha to help me with this analysis. I'm going to plot this function and look at different values of f. So here I'll change this to 4, and here I will do minus f, and of course f is not a known symbol, so Desmos wants to insert a slider, and we're completely fine with that. Let's just change our slider to go from 0.05 to 0.08 in steps of 0.01. Okay, there we go. We'll click done, and now we'll move this over here. So if we let 0.05 thousand or 50 fish be caught each month, then that suggests that we'll have two equilibrium points, 0.586 and 3.414. Now recall that if f was 0, we had equilibrium points of 0 and 4. Okay, but oops, I just changed that. 0.05. Okay, but now notice what happened. When I'm starting to fish, I've really closed that interval on which the population has opportunity to grow. So my carrying capacity, even though it's 4, the maximum number of fish my population can support is only 3.4. And that should make sense because we're fishing a bunch of them out of there. Right now, you might say, well, why isn't 0.05? Why didn't we subtract 0.05? Well, it's a little bit more complicated than that because this is a monthly fishing rate, which then naturally affects reproduction, right? Because those fish that we catch can't reproduce. And so it affects more fish than we might imagine. Also, if you have fewer than 0.586 thousand or 586 fish, then your population is going to go into extinction if you're going to fish at that rate. So we'll just say about 0.586 and 3.414. 0.586 and 3.414. Okay, so I'll draw here y equals 0.586 and y equals 3.414, and the population wants to grow on this interval. So still, this acts as the kind of updated carrying capacity, and we'll have the population wants to approach that steady state, and if you ever have fewer than 0.586 fish, the population will go into extinction. So if you wanted to allow this kind of fishing, you'd want to make sure that you started off with at least somewhere around 600 fish instead of 586 or below. Now if I increase this parameter just slightly and make it 0.06, let's see what happens to the equilibrium points now. And I can just come over here and drag this slider to make it 0.06. And now let's see what happens. So now my equilibrium point, oh look at that. So now I have to have at least 735 fish, because if I have fewer than that, my dy dt will be negative, and that means that my population will go into extinction. And now that I'm fishing more, my carrying capacity has been decreased sizably. 0.735, 3.265. And 3.265. So those have just come together. And once again, the behavior surrounding them has not changed. So that means there's no bifurcation that's occurred as a result of me changing that parameter. And now if I go to f equals 0.07, which I will do here, and just drag this to 0.07, once again, those equilibrium points have squished in even further, and now I have an even smaller window of growth, 0.9 and about 3.1. So here we are at about y equals 0.9 and y equals 3.1. Again, tiny window of growth here in comparison to what we had with less fishing. But notice that again, the quality of those equilibrium points, still one is a sink and the other is a source. And finally, if I look at f equals 0.08, let's see what happens here. If f equals 0.08, those equilibrium points have moved in even closer, 1.106 and 2.894. 1.1, and we'll just say about 2.9. And again, same behavior, small window of growth. And if your population unfortunately drops below 1,100, at that fishing rate of 80 fish per month, they're not gonna make it. Now we want to look if there's a bifurcation value. Now one of the things I see is that eventually these two equilibrium points will squish together based on what's going on here. So let's change this to something a little bit higher. Instead of 0.08, let's go up to 0.12 and see how that changes things. Okay, there's 0.09. Oh, wait a minute, what happened here? If f is 0.1, now I'm not going to draw this, this phase line for f equals 0.09. When f is equal to 1, I only have one equilibrium point, and that equilibrium point occurs at y equals 2. So at y equals 2, now I have one equilibrium point, and notice that to the left of y equals 2, dy dt is negative. Our graph is below the horizontal axis. It is a negative vertical value. And when y is bigger than 2, dy dt is also negative. So notice that now not only do I have just one equilibrium point, but that equilibrium point is neither a sink nor a source. It is now a node. So f equals 1 is the bifurcation. That's the bifurcation point at f equals 1. If f becomes bigger than that, look what happens. And we can kind of see what this parameter is physically doing to the graph. It's really just shifting it down. It's shifting the whole parabola down. And if I make it any bigger than 0.1, oh, I'm sorry, this should be 0.1, not 1. It should be a 0.1 right there. Then the population will go into extinction. Notice that I have no equilibrium points anymore. So f equals 0.1 was sort of that one indication, or that one point where we went from having two equilibrium points to having one equilibrium point. And by our definition of bifurcation, we have satisfied it. Now, hunting for these is not always trivial. One of the things we can do is just play around with the value in something like Desmos, and we can find it that way. Another thing I can do is we know that really this parabola will, once the vertex shifts down, which started out at let's see, I make this 0. When we weren't fishing at all, notice that 0.1 was the value of the vertex, or the output value of the vertex. So if I shift this thing down 0.1 units, well, that's going to bring the vertex down 0.1 units, and that's where we're going to have the bifurcation value. So you can find this mathematically as well. If you kind of get real clever with the algebra and, okay, what transformation are we performing by subtracting this parameter off, then you can solve for this bifurcation value mathematically. The way we did it was just by experimenting and seeing, geez, if I make this value bigger, it looks like eventually these two equilibrium points may merge into one. And once again, what you'll see in a bifurcation plot is you'll see somebody actually connecting these points. This is going to be really sloppy, but it'll kind of look something like this, so that you can sort of see that anytime you're within the confines of this curve, that's where you have that small window of growth, and when you're outside of this almost like horizontal parabola, then you have pockets of decay. So that's really the holistic story of doing this equilibrium analysis. It leads to more powerful analyses which can start off or spawn this bifurcation analysis. And we've already done this with solving with the parameter intact. So we could solve this differential equation with f in there and then have a solution that involves f, and then experiment with the actual solution curve. But notice that we didn't need to do that. We did a bunch of different analyses without ever solving the equation.